All right, if we have two normally distributed sets of test scores in which the higher score generally indicates a better result, to compare scores on two different tests, say we have the SAT and the ACT, in relation to the mean on each test, we can use actually the z-scores. And what happens is the better score is the item with the greater z-score. So you might have like a really good number for SAT, but your z-score is less than the z-score for the ACT, and so your ACT actually is the better score. So using z-scores, that can tell us what is the better test score. And that's the example we have here. So the SAT has a mean of 500 and a standard deviation of 100. Now the ACT, on the other hand, has a mean of 18 and a standard deviation of 6. Both tests measure the same kind of ability with scores that are normally distributed. Suppose you score a 550 on the SAT and a 24 on the ACT. On which score did you have the better on which test did you have the better score? All right, so SAT, ACT. Well, Z in this case, so if we scored a 550, that's going to be our data, minus the mean, which she said was 500. Here they said the standard deviation was 100, so that's going to be 50 over 100, so that's going to be a half. So our Z-score in this case is a half. Now for this one, Z is equal to what? All right, so we have 24 minus the mean, which is 18, all over the standard deviation, which was 6. Well, that's 6 divided by 6, which is 1. So here our z-score is 1. So which test did you score better? Well, we scored better on the ACT. That was the one we scored better on because we had a 1 for a z-score versus only the half for the SAT. Okay. What about this one? Use the information from example 5, which is kind of this second part of the thing, to find the IQ corresponding to a z-score. So this time they give us a z-score and we have to find the IQ. All right, so remember z is equal to the data item, which is what we're looking for, minus the mean all over the standard deviation. So those are all the items we're looking for. So for A, we get a negative 2.25 equals x minus. Now the mean, they say, is 100, and the standard deviation is 16. So now we have to solve for x. So now you have to remember your algebra. So I'm going to first multiply the whole thing by 16, because when I multiply this by 16, it cancels. So now I take a negative 2.25 times 16, and I get, I don't know, so we'll see, negative 2.25 times 16, and I get a negative 36. So I get negative 36 equals x minus 100. Now, if I add 100 to both sides, I get, on this side, I get a 64 is x. So my IQ here is equal to 64. And this is for part A. Part B, well, I would expect that because I had a negative here. So it's going to be below the mean, which was 100. So I got something below the mean, so that makes sense. So now this one is a positive z-score, so I better be greater than the mean. So I better get something greater than 100. So here, if I get 1.75, and that's going to be equal to x minus 100 over 16. Similarly, I multiply both sides by 16. So now I have to take and multiply 16 times 1.75, and I get 28. So I get 28 equals x minus 100. Add 100. So 128 equals x. So here my IQ is equal to 128. So that's what we were looking for in these. And again, the whole key was, could we plug what we need to into the z-score formula and then solve for one of the variables? So they could have given us any of these, and except for one, and we could have solved for any of that one that was missing. So they could have gave us the top three. We solved for the standard deviation. They could have gave us the z, the x, and s. We solved for x bar, but they gave us a z, the x bar, and s, and we solved for the x. Okay, so that's one of the things where you have to remember how to do your algebra to be able to solve those problems. All right, so let's stop there and we'll come back for some more.